Hello students. Uh, Today I am going to discuss one very important problems on fluid dynamics, fluid mechanics, that is fluids rotation in a cylindrical container. Okay. For this, uh, suppose the fluid is in a container. So initially the fluid height is this much, but when it is rotating with some angular speed omega, then for any fluid element, it will have a centripetal acceleration towards the center of this axis, because all the fluid particle will rotate in a circle. So all the fluid particle will must have a centripetal force towards the center of this circular part. Okay. So as we know, when a steady fluid in a container, okay, it will accelerate along this direction A, then for any fluid particle it will have an acceleration A in this direction. গতিকে এইটো direction যদি acceleration A থাকিব, তেতিয়া আমি যদি চাও normally কি হয়, এটা same height pressure to same থাকিব লাগে। কিন্তু if আমি যদি চাও, if we look at this particular element, then there will be pressure like this. Okay, P2A, suppose area of cross section of this fluid element is A, and pressure from this is P1, then here the force will be P1A. So if we write the force equation for this particular cylindrical element of the fluid, then we'll have pressure difference P1 minus P2A is equal to, because this element is moving with an acceleration of A along this direction, so it will have a particular acceleration, so it will be equal to ma. So from this we can say that P1 and P2 is not having the same pressure, so P1 is having the more pressure than P2, so its surface will become like this. Okay, surface will become like this. So this point will be at the higher height, and this will be at a lower height. Okay, from the free surface, the free surface will automatically take this particular shape of the shape. Okay, so from this, when a liquid will be rotating, then here you see when it rotates, যেতিয়া rotate কৰি থাকিব, প্ৰত্যেকটো liquid particle কি হ'ব, প্ৰত্যেকটো regionত এনেকুৱাকে circle move কৰিব with some angular velocity omega. Then when it moves with some angular velocity omega, then you see for this element which is at a distance, small distance from the axis, then it will have a centripetal acceleration as r omega square, which varies with r. So the acceleration will vary with r. As acceleration vary with r, we can say the pressure difference between different points will be different, so it will go on increasing like this. So surface will take, if you consider all the points, all the fluid elements, our surface will become like this. Okay, our surface will become like this. So for a rotating fluid in a cylindrical container, if it is rotating with angular speed omega, then it will take the surface, it will take the shape of the surface like this. Okay, now let's analyze the pressure at a particular point at a height h from the center of the free surface of the liquid. So this is the center of the free surface. Though as already I have explained this, why the free surface takes this kind of shape. Okay, so this is the center of the free surface, and let us take one particular element at a height h from the center and at a distance r from the axis of the rotation. Okay, this particular element, let me take it out. Okay, so this is our element. So let the area of cross section be A and its length is dr. Okay, it is along the radius vector. So its volume will be dv, will be a dr, is it? So its mass will be dm equal to density, because it is a fluid element, so density of the liquid itself or fluid itself, rho a dr. This will be your mass. Now if we analyze the force diagram for this particular element, here will be pressure like this, let it be P2, and here will be pressure like this, let it be P1. Okay, so if we write the force equation for this, since it is rotating with hand, this element particular element, name it as a element, is rotating with some angular speed omega, so it will have a net centripetal acceleration towards the center of the towards the axis. Okay, so if we write the force equation for this, then we will have P2a, the force at this point, and minus P1a, force at this point, is equal to mass of the element, that mass of the element dm into acceleration, that is centripetal acceleration. Since this element is at a distance r from the axis, so it will have r omega square, since every fluid particle or every liquid particle here is rotating with an angular speed of omega. Okay, so we will have, if we put these values, P2a minus P1a is equal to, put a value of dm from this, rho a dr and r omega square. Okay, so from this we can have this P2 minus P1, it's a small pressure difference, and we can cancel out this a, so we're left with rho omega square, since omega is constant, r dr. Okay, so this is our particular equation for the pressure of this particular element, pressure difference. Since this particular element is very small, so we can take this as dp, so we can take this as the point element at a height h from this, at a height y from the, at a height y, at a height y from the free surface. Okay, this element is at a height y from the free surface, so this dp will be equal to rho omega square r dr. So we are left with, if we integrate this, we need to integrate this to get the pressure variations. So integrate this, dp is equal to p, and we will be left with rho omega square integration r dr. So this will be equal to rho omega square r square by 2 plus 1 integration constant. Okay, so we are having the pressure difference or pressure at a point, we can say that. So this is an integration constant c, so we need to find out this integration constant. So the pressure, we can say that the pressure at a height, at a point at height y from the free surface of the liquid, free surface of the liquid, is p equal to half rho omega square r square plus c. Okay, so this is our equations, but we need to find out this c, so let us find out the c. Okay, okay, for this integration constant, what we have is that, so this was our cylindrical container. Okay, here we have this particular axis, so from this it is having this particular shape of this surface. So let uh, you see at r equal to 0 we have pressure. At r is equal to 0 we have pressure P is equal to, you see it is at a height h. So from the Pascal's law, if the pressure at this point is P naught at the free surface which is exposed to this atmosphere, it is P naught here, and so pressure at r equal to 0, you see P equal to P naught plus rho z h from Pascal's law. Okay, according to this, then we can put in this particular equation number 1. So P is equal to P naught plus rho z h is equal to, for r equal to 0, it will, this term will be equal to 0, so for C. So from this boundary condition, we can have the integration constant C value as P naught plus rho z h. Now put this value here, P is equal to half rho omega square r square plus rho naught plus rho z h. So this is our final expression for the pressure at any point at a height y from the free surface of the liquid. Okay, free surface of the liquid or the fluid, and here h is the height of the element from the center of the free surface. Okay, now for the equation of this surface, okay, for equation of this surface, what we can do, let us take any element y of the distance y. Okay, here the pressure is P naught again. So for this point we'll have if it is at a distance r from the axis, so the r distance দূৰত থাকে তেতিয়াহলে a point for any point at a height y from the free surface, that will have a pressure. That means that r is equal to r, and at a height y from the free surface, we have the pressure at this point will be equal to how much? P naught plus rho zy, and this will be equal to half rho omega square r square plus P naught plus rho g h. So from this we are left with P naught got cancelled. So if you take common rho g, y minus h is equal to half rho omega square r square. So we are left with y minus h is equal to half rho omega square r square divided by rho z. So we are left with half omega square r square by g. Okay, so this is your equation of the surface. Okay, it is parabolic again. So half omega square r square by 2g. Now for this element, here this is your maximum height between the center and the edge. So for this point, for any element here, the h, this h was our height of the height. This is the y max. So for maximum height difference between center and the edge of the free surface, if we look at this, for this particular element, it is at a maximum height from the free surface. So for this, the height of the element from the free surface is 0. That means here we can say h equal to 0. If we take h equal to 0, then we get the maximum height of the element from the free surface, that is y max can be written x is equal to half omega square r square by 2g. So this is all about the rotation of a fluid in a cylindrical container. So I hope you have understood. So what we have learned, pressure at any point at a certain height from the free surface, certain height h from the free surface, and at a distance r from the axis of rotation. Okay, so that is equal to P equal to half rho omega square r square plus P naught plus rho z h. Okay, and then the equation is y minus h equal to half omega square r square by g. So this is your equation. Then last, the maximum height difference between center and the edge of the surface is your y max is equal to half omega square, putting h equal to 0 and r equal to capital R, that is radius of the cylindrical container, r square by g. Okay, so this will be your maximum height difference between the center and the edge of the surface. Okay. So we are in particular one equation I did maximum height difference, that it should be r square, capital R square, h is equal to 0 and r is equal to small r. Okay, so I hope you have understood. Thank you.